Well, thanks, and I really appreciate your forbearance for letting me back up here again. In 1993, I believe, I was one of the many PIs on a proposal to put an array of seismometers at something like TA spacing over the middle quarter of Alaska. And it's nice to see that this is finally happening. This is very exciting as a seismologist who's been working there for a long time, that this incredible resource is on its way. And so I want to just take some time right now to think about what are some of the targets, some of the things we might see based largely on results from recent both passive and active source experiments. And the map on your left is showing some of the main various PI's Pascal arrays that have been done. Of course, the obvious big thing, and Ken just ended with this same slide, is there are volcanoes and there are earthquakes. This is most of North America's earthquakes are on this map, not on the maps in the lower 48. And the rupture areas of many of the largest earthquakes in the world are shown on here. This whole plate boundary is ruptured, almost all of it between 1938 and 1965, including in the Gulf of Alaska. The Good Friday 1964 earthquake is, of course, still probably arguably the second largest earthquake we've ever recorded. Because of this, not just EarthScope, but I should also say Geoprisms is moving up there as its next focus site in subduction. And I was told to plug a workshop before AGU to go and discuss Aleutian Alaska logistics. Anyway, big earthquakes are going to pose tremendous research opportunities. The volcanoes do as well. They also pose some logistical challenges on their own. Something like 80% of all U.S. earthquakes occur in Alaska. This is going to be far more stuff to ingest through the TA than anything that we've had to deal with before. And there are a lot of faults at a lot of different depths. They're very interesting to look at. To sort of put this in perspective, Mike West passed me this among some other figures. If you can see this is showing the cumulative moment from earthquakes in the last 50 couple of years. Of course, most of it's the 1964 Good Friday earthquake. The 1965 Rat Islands earthquake makes up most of the rest. And then if you go through all those yellow, orange, and red pie slices, those are just other Alaska earthquakes that happen every year. And that little tiny gray sliver, that fraction of a percent at the end, represents the lower 48's contribution to seismic moment. So it will be a challenge. To illustrate this, I was going to show you some results that we just submitted last week from the Moose experiment. This is, what do you call it, multi-something or other observations of subduction. It was an acronym that made sense at some point. But anyway, in the first 13 months, we had 34 stations, the black squares on this, running continuously. We recorded 12,618 earthquakes that we could locate in the network. That works out to about 31 earthquakes a day. Probably catalog completeness somewhere around magnitude 2. So this is order 10,000 earthquakes of that size. This is in a small patch. A little arrow is showing the TA grid spacing nominally. This 85 kilometers they're doing. So there will be earthquakes. Is sort of one point to make. And of course, there's going to be other cool stuff too. We know that there's a lot of tremor and lurking. Very little has been done about it yet. And so it's shown on your left is a map from Peterson and Christensen showing Ota et al.'s slip area. This is a slip patch just north of Fairbanks. The moment equivalent is about a 7.2-ish with some of the tremor. These things are big and they take a while. I just found out earlier this week that we're in the middle of another multi-year slip episode in around the same place. Farther out in the Aleutians, Justin Brown just published a paper showing with various volcanoes arrays that there's a lot of tremor pretty much everywhere you look. So we'll be seeing some of that stuff too. And that's otherwise wide open. Mostly I want to talk about structure and imaging. This is showing most of the both active and passive source experiments that have traversed the sort of the subduction zone in the forearc in the last couple of decades. As you can see, start saying a couple words about the active source work first. After 1994, where this thing crossing through the Aleutians went, there was really almost no major active source work until the 2008 steep profiles, and that's been about, so there's been very little of that offshore or onshore. But prior to that, there's quite a bit. So in the 1980s, I think several universities and USGS coordination conducted this TransAlaska Crustal transect. This is an active source imaging thing that marched its way along the pipeline from Valdez to Prudhoe Bay, as you can see. And this is sort of the compilation of all the crustal wide-angle refraction transects that Jerry Fuis published a couple of years ago. And it shows really nicely, sort of the whole way in which, in one transect, you encapsulate the building of a continent, from the southern active subduction margin to the accreted terrains to sort of the Paleozoic interiors. You don't quite get to the Archean, to sort of some other weird thing in the north that happens on the Bering Sea side. But one of the things that sort of struck home when this came out is that, this really shows well that these terrain-bounding faults that are on the surface are really the tops of these shallow dipping, things that have been accreted through a process much like modern subduction. The Yakutat terrain is the one that's actively colliding right now. Ken showed you some of this offshore. But we don't really know that much about what happens to these things below the depths at which these crustal images are made. So I think one of the big exciting targets will be to think about the deep structure of terrain accretion and how continents are built from an active subduction margin all the way into, on the Canadian side, you can get into Archean shield. What is this thing that's subducting now? Well, this geodetic data suggests a lot of it's kinematically connected, at least to 80%, moving with the Pacific plate. Recently, this is from Worthington et al., 2012. The steep profiles sampled with, this is active source work done off the Langseth, fairly well. What this gives a much better idea of what this stuff is made of. So this is the Pacific plate. This is the tail end of the Aleutian megathrust. And so this is this area of the collision that you just heard about. What this looks like, based on this, is something like this. It was 15 to 20 kilometers thick of stuff that has velocities in the high 6s to low 7s. The velocity column looks a lot like oceanic plateaus we see around the world. So the presumption is probably some kind of oceanic plateau that is driving the collision, at least in the west and east and central parts. And as we'll show in the west, some of this may be subducting. We think we know this from some of the sort of first results we got from these broadband transects. So I'm mostly going to concentrate on these two. Doug Christensen and I and a number of other people have been in this room have worked over the years on the broadband experiment across the Alaska Range. That's bear and moose, which I told you about before, that were designed really to do this kind of sort of 10-kilometer spacing, high spatial sampling of teleseismic wave fields and local wave fields and so on. Marching down the Alaska slab. So this is where seismicity is 50 and 100 kilometers deep and peters at. Mostly what I'm going to show you is sort of transects along this. And this is showing on your left what the sort of back projection of receiver functions, where we saw right away we're seeing very strong signals from the same depths as earthquakes. Earthquakes are the yellow dots here. That showed what looks to be the top and the bottom of a low velocity channel with a lot of analysis of those, and later migration of the scattered wave field. What we see is 15 to 20 kilometer thick, low velocity, what looks like subducted crust. This thickness is very similar to what the active source data showed offshore. It would suggest they're actually imaging a subducting oceanic plateau that's just barely thin enough to be subducting and not accreting, down to at least depths of 120, 130 kilometers. The depth limit probably has more to do with eclipsization kicking in, especially if the dates that Ken just said for when this collision started were 30 million years ago. So this is sort of been the first one of the big things that we've learned. There's a lot of other structure, though, in the Mantle Wedge we don't know that much about. This is sort of the farthest north we've gotten. And so one of the interesting targets for US Array will be to figure out, how much of the rest of this really has to do with subduction, how this is sort of evolving into a subcontinental mantle of kinds that we see elsewhere in North America. This is just sort of the cartoon of this. We've now extended this migration. This is the same map turned on its side, bear, moose. This is that same subducting crust. Here is shallower depths. Low velocity layer continues, but it's much thinner. It's much lower. It looks like, based on what the seismicity is, based on what the geodesy is telling us, that this is actually, the rupture, the this is the plate interface. This is right through the part that ruptured in 1964. We're seeing very low velocities, some combination of subducting sedimentary channel, high pore fluid pressure. We're busy analyzing this right now to try to understand it. But what you can see is, this is really, spectacular images of subduction in action, how the subduction makes the continent. And we also are able to look at things like these edges of these terrains. So we have this one cross line on the Kenai Peninsula where we're able to see a big difference between the stuff sort of on the Yakutat side here, and then it seems to end at depth somewhere in the middle of the Kenai Peninsula, where we're seeing somewhat thinner, low velocity, something that looks a lot more like oceanic crust. We would suggest that this is the boundary between the Yakutat crust and simple Pacific plate subducting here. And this is a piece of one of these old active source lines offshore. One of the things these images do, besides tell us about terrain subduction, is they give us a very nice control of the geometry of the plate. And together with other things, we can actually make a lot of inferences about the thermal state and the flow in the plate. And so we take these geometries. One of the other things that we did, the Bear did some Stachnik 2004, there's very strong variations in seismic attenuation. This is based on S-wave body waves. We're able to image factor, this is in these horrible units of 1,000 over Q, but this is Q's less than 100, and these are Q's over 1,000, maybe. So maybe a factor of 20 variation and attenuation at mantle depths between the shallow part of the forearc and the deeper part of the mantle. We think is a very good proxy for temperature and telling us we're seeing the boundary between the hot flowing part of the mantle and this what we call cold nose, a piece of the mantle wedge that sits out there. And so we can use that together with this geometry and some ideas of rheology to make sort of geodynamic, this is a kinematic thermal model, and I think in the next talk we'll hear a lot more about other approaches to this. But the point is, this gives us a fairly decent idea of what parts of the mantle might be flowing and what parts might not be flowing, and we can learn a lot about, say, earthquake conditions. One last bit of this story, though, sort of thinking about the differences in the crust and mantle that you might see, say, underneath this part of the array, under the Kenai Peninsula, and then back here, somewhere north of the Alaska Range. This has been a very important sort of framework to think about the anisotropy that we're inferring from shear wave splitting. This is showing a compilation of SKS fast directions from Bear, Moose, and the Arctic experiment that continued up to the north coast. And what we can see is that it's really, in some respects, a very simple pattern of anisotropy that we would infer. That in the south, as far down to the south coast at least, some offset there, and then in through Anchorage and somewhere about where the slab is about 70 or 80 kilometers deep, we're seeing fast directions that are in the direction of Pacific North American convergence, so in the direction of plate motion. These change abruptly by about 90 degrees to seeing these things that are now perpendicular to the convergence direction, and which this pattern continues, all the way up past where you're seeing subducting slab, all the way up to the north coast and the 1 or 2 points we see west. Now, there's a single linear transect. We don't really know much about the 3D geometry. Obviously, the TA and other experiments on top of this is going to tell us a lot more about this. But it really suggests that there's sort of two models for how we might think about flow and anisotropy and what's important. One is, and this is what we had published a couple of years ago when we first showed the first bit of this data, is that we're really looking at the effect of the mantle wedge. So underneath these lines, this orange blob is that highly attenuating part of the mantle wedge underneath north of the Alaska Range. The colors here are indicating the orientation of the fast directions. So this is, the blue ones are normal to the slab, so in the direction of convergence, and the red ones are normal, are parallel to that, perpendicular to those other ones. And you can see this transition happens right where we're entering the hot flowing, what infers the hot flowing part of the mantle. So the suggestion is that this is really a reflection of seeing mantle flow here and seeing something else maybe in the dangling plate there. But this continues all the way across Alaska. And what complicates this is that if we look at sort of other notions of what controls flow, these two directions are also notionally parallel to the absolute plate direction of, in the south, the Pacific plate, and depending on the reference frame, in the north, the North American plate. Now, North American plate velocities are pretty low up here in absolute frame, but be interesting to think about how these patterns go. And it really sort of points to this kind of dichotomy. What we think is really important in sort of controlling mantle flow around subduction zones. Is it the slab in the subduction zone itself? To what extent does the global flow field play an important role? Hopefully you'll hear more about this from the next talk, but it does suggest there's a huge role to be playing in continuing these experiments spatially across Alaska into Canada. So I'll just end right there. I'll say, again, I'll read these. Almost all the seismicity in the U.S. comes from there. This is the place where terrains have been accreted and are accreting to build crust and presumably subcontinental mantle, perhaps. There are volcanoes, there's melting, and we're seeing a lot of evidence of some really interesting flow fields that should help us understand, how plate tectonics is driven.